this video, we will focus on bases and some of the common reactions that exist between bases and acids. So just to recall, according to our Arrhenius definitions, which we defined in our previous video, bases are substances that produce hydroxide ions in water. So these are things that have hydroxides in them, OHs, and when we put them into water, they will drop those OHs and leave them behind in the water. Now, some common examples of this. We have magnesium hydroxide. Magnesium hydroxide is common in the use of things like antacids and things. It makes milk of magnesia. We also have sodium hydroxide, better known as lye. And we have ammonium hydroxide, which is what happens when ammonia is put into water. Now, ammonia would be considered an exception to the rule when it comes to bases, because ammonia, while it does not have an OH on it, we do consider it basic because as soon as it drops into water, which is what has to happen anyway, in order for a base to form, that water reacts with the ammonia to make ammonium hydroxide, and the ammonium hydroxide then splits apart into ammonium ions and hydroxide ions. So that's what bases are by their definition. Now, when it comes to nomenclature of bases, for the most part, we are thinking about things in terms of hydroxides, and so hydroxides are ionic. And the result of that is that most of the compounds that are bases are ionic compounds of some kind. And so the name of the compound is simply the metal that is attached to the hydroxide and then hydroxide. And so there are lots of bases that fall into this kind of categorization. But the ones that you need to keep the biggest tabs on are these six: magnesium hydroxide, lithium hydroxide, which is a common component in lithium-ion batteries, sodium hydroxide, which again is lye, potassium hydroxide, potash, ammonium hydroxide, ammonia, and aluminum hydroxide. So let's look at how some bases are made and how they're used. And so if you recall from our video on acids, acids are formed mostly when non-metallic oxides, so we burn some sort of element that is non-metal in oxygen, it forms a non-metallic oxide, and then we take that non-metallic oxide and we dissolve it in water. And it reacts with the water and it forms the acid that we seek. Well, a similar process is used to make bases. The only difference is that instead of a non-metallic hydroxide or non-metallic oxide, we end up making a metallic oxide. Now, the metallic oxide can come to us one of two ways. First of all, most metals exist in oxide form when we dig them out of the ground. Very few metals are actually found in their true elemental state. Most of them react with oxygen because oxygen is abundant. It's the most common element in the Earth's crust, and it forms a very stable compound. So that's one way. The other way is that you could take that pure metal sample and you could light it on fire and form the oxide that way. But either way, regardless of the origin of the oxide, if you react it with water, the result will be a hydroxide, a base, and hydrogen gas. And so some common uses for bases, as I mentioned before, lithium hydroxide is often found in lithium-ion batteries. So anything that has a long-lasting life, watches, hearing aids, computers, iPhones, those kinds of things usually run on the lithium-ion batteries. Potash is predominantly found in liquid-based soaps. Potash and lye are both very strong contributors to a reaction class called saponification. Saponification reactions are common in the soap making process, and depending upon which one you use, the properties of the soap are going to differ slightly. So sodium hydroxide is used generally for bar soaps, As the soap forms, it kind of cakes up and solidifies, and you press it together and it makes a bar of soap. For the potash, it tends to be a little bit looser in terms of when it solidifies, and you end up getting more liquid-like soaps. We also find lye in drain cleaners, so like Liquid Plumber, Drano. Often we use sodium hydroxide along with bleach and some other things to clean your drains. Ammonia is found in fertilizers. Magnesium hydroxide is the primary component of milk of magnesia. And aluminum hydroxide are found in a lot of different types of antacids, especially the non-calcium based ones, so your Rolaids and some of your other brands. Some general properties of bases. In general, bases do not taste good. They taste very bitter. They feel slippery, and that's not necessarily because of a property that they hold themselves. It's actually a reaction that is taking place on your skin as you interact with the base. So when you touch a base, what happens is that the hydroxide starts reacting with the oils on your skin, with your skin surface itself, and it creates this soap-like kind of feel. And so you're literally making soap in between your fingertips with the base. And if it keeps going, it goes from being slippery to actually starting to hurt. Just like with acids, we see electrolytic character out of bases because we know that bases will dissolve in water, and when they dissolve, they will form ions. So depending upon whether we have a strong base or a weak base, we'll get strong or weak electrolytic character. We also know that bases turn litmus paper blue. But what's really interesting about bases is that unlike acids for the most part, they're either always found in water or they're found in the gas phase, and they're in the gas phase they're non-acidic, and in the liquid phase they're completely acidic. With bases, almost all of them are found in solid form. And if you were to touch any of these solid form bases, you'd get some of that bitter effect, some of that slippery effect as it interacts with your skin. And if they dissolve in water, then those properties really become pronounced. Now, bases can also exist in the liquid and gas phases, but that's prominently more in the organic base kind of phase. And for that, we have to go beyond the Arrhenius definition. That actually gets into more of the other types of definitions that are far more general and beyond the scope of this course. As we saw with acids, bases are capable of reacting in a strong fashion and completely dissociating. And so we see in sodium hydroxide, we get 100% conversion. All of the sodium hydroxide molecules convert to sodium ions and hydroxide ions. And as a result of all of those ions present, we get a really pronounced chemical reaction. And we get a very strong electrolytic character as a result. Weak bases also exist. So ammonium hydroxide, we see, again, the rule of thumb we were using was less than 5% ionization for weak acids. And this is true for bases as well. So ammonium hydroxide gets about 4% ionization. So we still have ions in solution. And because we have ions in solution, this base solution will conduct electricity. But if I were to compare the electricity that is being conducted in this solution versus what is being conducted in this solution, the sodium hydroxide solution would be a much stronger electrolyte than the ammonium hydroxide solution. Now, when it comes to metals, there are three primary metals that will react with strong bases. And the solutions here have to be concentrated. They cannot just be dilute solutions. We have to have concentrated bases with one of these three metals. And the three metals are aluminum, zinc, and lead. Now, we don't see reactions with strong bases and steel. We don't see as much with things like copper or um, um, any of the other more common metals. It's really just kind of these three. And so that's again a big difference between acids and bases. The range of reactivity for acids is much more than the range of reactivity for bases. But when bases react with your skin, a lot of this should look familiar. This is exactly the same thing that we use to describe acid contact. We start to see a reddening at the site of contact. Where it changes is the stuff in the middle. In acids, we started to see scarring. We started to see kinds of blistering, like what you'd see for a heat burn. In base corrosion, we start to see that saponification reaction, the soap making reaction, where the skin's texture gets thick and sticky, and then we get deep wounds, and then we get irreversible tissue damage and disfigurement. So very odd, very different when it comes to how bases interact with your skin compared to what acids do. So let's take a look at some acid-base reactions. Now, the most common acid-base reaction is called a neutralization reaction. And when acids and bases interact with each other directly, what we get is a neutralization. And a neutralization always produces two things. First, we always see water. Water is always going to be a product of a neutralization reaction. The other thing that we're always going to see is a salt. And we got to remind ourselves here, the word salt isn't referring specifically to NaCl, just common table salt. That's just kind of the most common example that we have. When we think about a salt, what we really want to think about is any ionic compound. So if I can recognize that I have an ionic compound, that should trigger in my head that I'm talking about a salt. And so neutralization reactions are when we have an acid and a base reacting with each other to give a salt and water. And the reason they're called neutralization reactions is because the acidic effects of the acid and the basic effects of the base more or less cancel each other out in these kinds of reactions. Now, there are other kinds of acid-base reactions that can exist. For one, we have reactions with carbonates. Carbonates will give a reaction with acid that will produce carbon dioxide, water, and some sort of salt. And it doesn't matter what kind of carbonate it is, we'll always see the same kind of reaction. Carbon dioxide, water, and salt. The other kind of reaction, this is we referred to in a previous video as pickling. Here we have a double replacement reaction taking place where we have an oxide reacting with a water or an acid, and the end result is again water. Water is a key component of most acid-base reactions, and a salt. And so what's interesting about these reactions is that these we can get out of the ground. These are ores, metallic ores, things that we would find in mining. And if we react them, we can get them to separate from the oxygen, which is pretty tough to do otherwise. And then the resulting solutions of these salts, we can then use a process known as electrolysis and actually purify and extract the iron or the aluminum out of them for whatever purposes we might need those materials. So there are other reactions that are interesting and worth watching here. I'm going to post a long list of YouTube videos here on the end of this description where you can see some of the other kinds of chemical acid-base reactions in action. Until next time, have a good day.